problem involves a high current measured on a loaded 350 MCM cables feeding a temporary power supply with a variable voltage transformer bank. There are several possible explanations for the situation. Firstly, inductive loading could be the cause. When cables are carrying current in opposite directions, they create opposing magnetic fields. This magnetic interaction can induce an inductive load on adjacent cables, especially if they are in close proximity. Inductive loads can cause high current readings even when no resistive loads are connected. Secondly, capacitive coupling may be to blame. Cables running in close proximity can also experience capacitive coupling. This occurs when the electric fields from one cable affect the voltage and current in another cable. Capacitive coupling can cause currents to flow in unloaded cables. Thirdly, stray voltage is a potential issue. The high voltage from the transformer bank can potentially create stray voltage on nearby conductors. This stray voltage can induce currents in the 350 MCM cables even when they are not directly connected to a load. Fourthly, electrostatic discharge, or ESD, might be a factor. ESD occurs when there is a sudden release of static electricity. ESD can create transient currents in cables, resulting in spikes in current readings. Fifthly, measurement error needs to be considered. Faulty meters or incorrect measurement methods can also lead to inaccurate current readings. Now, let's consider some observations about the different configurations tested. In the baseline condition, the currents on the 350 MCM cables are higher when 2/0 loads are connected. This suggests that the inductive load is being imposed by the 2/0 loads. In change 1, with all 2/0 loads removed, the currents on the 350 MCM cables are still high at 1240 amps. This could be due to capacitive coupling or stray voltage. In change 2, removing one 350 MCM cable equalizes the currents on the remaining cables to 214 amps. This could indicate that the inductive load from the removed cable is balancing out the capacitive load or stray voltage. In changes 3 and 4, as more 2/0 loads are added, the currents on the 350 MCM cables increase again. This supports the theory that the inductive load from the 2/0 loads is the primary cause of the high currents. Based on these observations, here are some recommendations. Firstly, separate the 350 MCM cables from other cables as much as possible to minimize inductive loading and capacitive coupling. Secondly, verify that the transformer bank and measurement equipment are functioning correctly. Thirdly, consider using shielded cables or other measures to reduce stray voltage effects. Fourthly, ensure that all connections are tight and secure to prevent ESD. Let's delve a little deeper into each of these potential issues. Inductive loading arises from the magnetic field created by alternating current flowing through a conductor. When multiple conductors are placed near each other, the magnetic field from one conductor can induce a current in the adjacent conductor. The magnitude of this induced current depends on several factors. Firstly, the distance between the conductors. Secondly, the amount of current flowing in the primary conductor. Thirdly, the length of the parallel run. And fourthly, the frequency of the current. In this case, the close proximity of the 350 MCM cables and the 2/0 cables, combined with the high current levels, likely contributes to significant inductive loading. Capacitive coupling, on the other hand, occurs due to the electric field between conductors. When two conductors are separated by an insulating material, they form a capacitor. Changes in voltage on one conductor can induce a current on the other conductor through this capacitance. The amount of capacitive coupling depends on, firstly, the distance between the conductors, secondly, the area of the conductors, and thirdly, the dielectric constant of the insulating material. Again, the close proximity of the cables in this scenario increases the likelihood of capacitive coupling. Stray voltage refers to unwanted voltage potentials that exist in electrical systems. It can be caused by several factors. Firstly, improper grounding. Secondly, inductive coupling. Thirdly, capacitive coupling. And fourthly, leakage current. Stray voltage can create circulating currents in grounded conductors, leading to inaccurate current measurements. Electrostatic discharge, or ESD, is a sudden transfer of electric charge between two objects. It can occur when there is a buildup of static electricity on the surface, followed by a rapid discharge to another object with a different electrical potential. ESD can generate transient currents in cables, potentially causing measurement errors and even damaging sensitive equipment. Finally, measurement errors can arise from several sources. Firstly, faulty meters. Secondly, incorrect meter settings. Thirdly, improper probe placement. And fourthly, environmental factors. It is crucial to use calibrated meters and follow proper measurement techniques to ensure accurate results. Now, let's consider the implications of using a delta transformer bank with no ground. In a delta system, there is no neutral point connected to ground. This can lead to voltage imbalances and increased susceptibility to transient overvoltages. Without a ground reference, it becomes more difficult to detect and mitigate stray voltage problems. The absence of a ground connection can also increase the risk of electric shock in case of a fault. Therefore, it is essential to implement appropriate safety measures when working with ungrounded delta systems. To further investigate the high current readings, consider the following steps. Firstly, use a high-quality clamp meter to measure the current in each 350 MCM cable and each 2/0 cable individually. Make sure the clamp meter is properly calibrated and set to the correct range. Secondly, verify the connections at the bus bars and ensure they are tight and secure. Loose connections can cause arcing and increased resistance, leading to higher current readings. Thirdly, inspect the cables for any signs of damage, such as cuts, abrasions, or insulation breakdown. Damaged cables can leak current and contribute to stray voltage problems. Fourthly, measure the voltage between each phase and ground using a high-impedance voltmeter. This can help identify any stray voltage potentials that may be present. Fifthly, use a power quality analyzer to monitor the current and voltage waveforms over time. This can reveal any transient events, such as ESD, that may be affecting the measurements. Sixthly, try rerouting the cables to increase the separation between them. This can help reduce inductive loading and capacitive coupling. Seventhly, consider using shielded cables for the 350 MCM runs. Shielded cables have a grounded outer layer that can block electromagnetic interference and reduce stray voltage effect. Eighthly, consult with a qualified electrician or electrical engineer to review the system design and provide further recommendations. It's also important to consider the ampacity of the conductors. According to the National Electrical Code, or NEC, the ampacity of a 350 MCM copper conductor depends on its insulation type and the ambient temperature. For example, a 350 MCM THHN copper conductor has an ampacity of 310 amps in a 30 degrees Celsius environment. However, this ampacity must be derated if the ambient temperature is higher or if multiple conductors are bundled together. NEC Table 310.15 B2 provides adjustment factors for ambient temperature, while NEC Table 310.15 B3 provides adjustment factors for the number of conductors in a raceway or cable. In this case, the 350 MCM cables are run in free air, so the ambient temperature is likely to be the primary factor affecting the ampacity. The 2/0 cables also have an ampacity that depends on their insulation type and ambient temperature. For example, a 2/0 THHN copper conductor has an ampacity of 175 amps in a 30 degrees Celsius environment. Again, this ampacity must be derated if the ambient temperature is higher or if multiple conductors are bundled together. It is crucial to ensure that the conductors are properly sized to handle the expected load current, taking into account any derating factors. Overloading conductors can lead to overheating, insulation damage, and even fires. In addition to the recommendations above, it is also important to consider the grounding and bonding of the electrical system. Proper grounding and bonding can help minimize stray voltage and reduce the risk of electric shock. The NEC provides detailed requirements for grounding and bonding in Article 250, specifically Section 250.4. It requires that grounded electrical systems be connected to earth in a manner that limits voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines and thus stabilizes the voltage to earth during normal operation. Section 250.4 B requires that non-current carrying metal parts of electrical equipment be bonded together into the grounding electrode system to create a low impedance path for fault current. This helps ensure that protective devices, such as circuit breakers and fuses, will operate quickly to clear fault and prevent electric shock. In this case, since the transformer bank is ungrounded delta, it is particularly important to ensure that all metal enclosures and equipment are properly bonded together. This can help minimize the potential for stray voltage and reduce the risk of electric shock. Consider using a ground fault circuit interrupter, or GFCI, to provide additional protection against electric shock. A GFCI is a device that monitors the current flowing in the circuit and detects any leakage current to ground. If the leakage current exceeds a certain threshold, typically 5 mA, the GFCI will trip and interrupt the circuit. GFCIs are commonly used in wet or damp locations such as bathrooms, kitchens, and outdoor areas to protect against electric shock. They can also be used in temporary power systems to provide additional safety. In addition to the technical aspects of this problem, it is also important to consider the safety implications. Working with electrical systems can be dangerous, and it is essential to follow proper safety procedures to prevent accidents. Firstly, always de-energize the circuit before working on any electrical equipment. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, wear appropriate personal protective equipment, or PPE, such as safety glasses, rubber gloves, and insulated tools. PPE can help protect against electric shock, burns, and other injuries. Thirdly, never work alone on electrical systems. Have another person present who can provide assistance in case of an emergency. Fourthly, follow all applicable electrical codes and regulations. The NEC provides detailed requirements for the safe installation and operation of electrical systems. Finally, if you are not comfortable working on electrical systems, consult with a qualified electrician. It is better to be safe than sorry when dealing with electricity. To summarize, the high current readings in the unloaded 350 MCM cables are likely due to a combination of factors including inductive loading, capacitive coupling, stray voltage, and measurement errors. The absence of a ground connection in the delta transformer bank can exacerbate these problems. To address this issue, firstly, separate the cables. Secondly, verify the equipment. Thirdly, consider shielded cables. Fourthly, ensure tight connections. Fifthly, follow proper safety procedures. By taking these steps, it is possible to identify and mitigate the root cause of the high current readings and ensure the safe and reliable operation of the temporary power system. Also, remember that regular inspections and maintenance are crucial for preventing electrical problems and ensuring the long-term safety of the system. Regularly inspect the cables, connections, and equipment for any signs of damage or deterioration. Replace any damaged components promptly. Test the grounding and bonding system to ensure that it is functioning properly. And finally, keep accurate records of all inspections, maintenance, and repairs. This information can be helpful for troubleshooting future problems.